we have a graph of voltage against current, and we're trying to figure out what component can be represented by this diagram. So usually with these kinds of questions, the graph is I against V. So we're given I on the y-axis and V on the x-axis. So it might be useful to switch the axes around, redraw the graph, and then try and think about what component would fit that. So what we see from the graph is that if we think about how voltage, or what happens to current when voltage increases, in the beginning, when you increase voltage, the current increases by quite a large amount. But later on, the voltage, as you increase the voltage, the yield in current is not as big as it was for lower values of voltage. So if we try and sketch that on a new graph, this time of I against V, so we know that the current increases a lot to begin with, so that looks something like this, and then as time goes on, the increase in current is not as big. So our graph would look like this. Another way that you can think about that is whenever you reverse or flip the axes like we've done here, then the graph will be reflected in the line y is equal to x. So y is equal to x looks something like this. If we reflect this curve in that axis, it would end up looking a bit like what we have on the right. So then we want to think about which component matches this IV characteristic. So we can go through each one and then see which one matches. So for a diode, what happens is as you increase the voltage, then at some point, usually around 0.7 volts, the resistance of the diode will significantly decrease, and then you will have an increase in current. So that would happen around 0.7 volts. Again, this is I against V. So that's not what we have here, so it is not therefore a diode. For a filament bulb, our filament bulb IV characteristic looks something like this. I redrew that because I wanted to make sure I didn't make my line flatten out at the end. That would imply that the current is not increasing anymore. But that's not the case. As you increase the voltage, the current will increase, but it will just do so at a lower rate. So don't flatten it off too much when you're drawing these kinds of curves. So this would be our IV characteristic for a filament lamp, which is what we have on the right-hand side. So this component will be that, a filament bulb. So the answer is B. For the sake of completion, we can go over the rest of the options. So an ohmic resistor is one which, ohmic means that the resistance is not changing. So if the resistance is not changing, then it will just be a straight line through the origin. So this is V, or rather, well, it could be V actually. This is I, this is V. If we think of the equation V is equal to IR, rearrange for current, so we get current is equal to, I'm going to write it as 1 over R times V, so this is like Y is equal to mx. We can see our gradient would be 1 over R. For a thermistor, how it works is usually when you're told you have a thermistor, it refers to an NTC thermistor. An NTC thermistor is a negative temperature coefficient thermistor. And that's one where as the temperature increases, the resistance will decrease. So as our current and voltage are increasing, then the power dissipated in our component also increases. P is equal to IV. As these two things increase, then power will also increase. As power increases, the temperature of the thermistor will also increase. Because if you're dissipating more power in a component, it gets hotter. So as the temperature increases, for an NTC thermistor, as we mentioned earlier, the resistance will go down. So if the resistance is decreasing, that means we should be getting a greater yield in current as voltage increases. So our graph would look something like this. Initially, the current is not increasing very much for a certain interval of voltage, and then later on the current increase will be greater for the same interval of voltage. And it's the opposite on the other side. They don't have a direction, NTC thermistors, so the same effect will occur if you were to reverse the component.